nuclei are so cool. So it's a great pleasure to introduce Gnech from Ulm University. So please.
Okay, thank you very much. Thank you for having me. So this is when you have a workshop, you always have weird talk. This is the weird talk of this workshop. And I'm going to talk about nuclear physics. I'm from Old Dominion University. Maybe I'm also affiliated with Jefferson Lab that is down the coast. If you never heard, it's just an electron beam accelerator where they study mostly the inner structure of protons, neutrons, and nuclei. So the actual talk today was supposed to be given by Alejandro Kesky, that maybe you know him. Unluckily, for personal reason, he could not come. Clearly, I'm not Alejandro, and so this means that. Sorry about that. I have some. Okay. So it means that my talk will be a little bit different. So I did my PhD in the PISA group, so where Alejandro is part of it, even if my supervisor was Professor Michele Viviani. And the results that I'm going to show you today are actually the collaboration of these three big groups. Mostly what I did was using the neural network quantum state that I'm going to present in a moment. I really hope you enjoy neural network quantum state. I don't know if you ever heard about that. It's a very new method based on neural network to compute, for now, ground state of nuclei, but also can be used also in atomic physics. Is very general. So why a nuclear physics physicist is here? Well, the reason is that we have something in common. A lot of the system that you study lives in the unitary window, and this is the case also for nuclear physics. I mean, you know that when we talk about strong force, we should talk about quark and gluons, but these are confined in neutron and protons, and the residual interaction that remain between neutron and protons is very peculiar because it happens to live really in the unitary window. So very large scattering length, very shallow state, in particular the deuteron. And this means that all the symmetries that are associated with the system being in the unitary window should also, and appears also, at the level of nuclear physics, even if we are not at the unitary limit. So we need to be a little bit careful. And luckily, we cannot play with the interaction at all. You have a little bit more room, and the system, you have more system. We are fixed with the nuclear interaction that we have. But the question that, let's say, Alejandro and a lot of us started to be interested in is that the fact that the nuclear physics lives in the unitary window can explain also all the nuclear charge. So the actual question is it enough, the unitary window, to explain that all nuclei, all the structure of all nuclei? So what we are doing with Alejandro is to go a little bit beyond the 2 and 3 body system and see if that, having an interaction that describe the unitary window and see somehow how from the unitarity we arrive to the nuclear charge. Somehow find like kind of the path that we want to. So, yes. Okay. So again, this is the talk of Alejandro. I actually got told by Alejandro what to say. So I'm going to be very careful. So usually you have very long scattering length. So technically is infinity. And then is the ratio with the actual range of the force. Oh my gosh, sorry. It's very long. Yeah. Okay, it should be better, right? Okay, and so the ratio between the effective range of the force and the scattering length has to be, I think, smaller than 0.5. And this is kind of defined in the unitary window, so where this kind of symmetry appears. For nuclear physics, this ratio is around 0.3. So that's the ratio of between the scattering length and the effective range. And that's why Alejandro really likes this, because he says, okay, we have this symmetry that for nuclear physics, this is what we would can define an accidental symmetry. It's just because it's there. It's nature that put it there. but it seems crucial. I mean, when we construct the nuclear interaction, particularly in the last years, people were very interested in nuclear interaction that does not involve the exchange of a pion. They call pionless effective field theory. The problem is that if you do a straightforward pionless effective field theory, this theory practically can describe the tritium, the helium-4 very well, and nothing else, because it collapses. It really collapses. You cannot, practically all the, let's say, that is like your initial point of your expansion of the theory, and for all the nuclei beyond helium-4, practically you don't, let's say this point is in the continuum. It's not a bound state anymore, and this creates a big problem. But the thing that actually the theory, the leading order of this pionless effective field theory does not have is the effective range. So it contains already practically a lot of the characteristic of the unitary window, but it does not like the scale of the interaction somehow inside. And what Alejandro is proposing, and I'm helping him mostly to do like the calculation, is really to see, okay, if we include at this leading order also the interaction, can we describe nuclei with the simplest interaction possible? And the interaction that we are dealing with is very simple. So this is kind of how pionless effective field theory looks. It's just nucleon that interacts in a contact interaction. And clearly we need also three body forces. So the two pieces here, this one and this one, are the singlet and the triplet. So the spin is 0 and 1 for the two nucleon. And these are just the projector on them, so nothing else. And you see that there are some low energy, we call them low energy constant, but some constant that we fit to usually, so in particular we fit them typically to the scattering length and the deuteron binding energy. They are related to each other. So these are contact interactions, so they have a delta, Dirac delta here, but for practical purpose, these are Gaussians. We need to smear them. And when you smear them, you can have whatever range you want. I mean, technically, it's like a construct of the theory. But if you do it in a smart way, you can select the range of this Gaussian to match exactly the effective range of the nuclear theory. So that's what Alejandro and actually Rocco Schiavilla did I mean, I was part of this, I did mostly the calculation, but I was part of this paper too. And clearly we also need to include three body forces as well. Also in this case we have a range, and this is not fixed. We use two different kind of reasonable for what we need. And the constant in front is made to reproduce the tritium binding energy somehow. Practically the idea is to somehow match what happens when in the Efimov physics as well. So if you use this kind of simple interaction, well, this is the number of nucleon, and this is the binding energy of the nucleon divided by the number of nucleons. So this is so all the nuclei more or less in nature will stay on this green curve that is called liquid drop model, if you remember, for nuclear glass. And using that simple interaction in that paper, what we show is that actually most of the nuclei, so we computed, they practically at leading order using practically reproducing the effective range, you are able to reproduce within 20–30% the liquid drop model. I mean, the calculations are very expensive. We did, if you are familiar with computational method, this calculation in particular, these last four have been computed using the auxiliary field diffusion Monte Carlo. But it's a Monte Carlo method. But that is not the greatest method in any case, because let's say it relies on the fact that the shell are closed. So, so we wanted to go a little bit beyond in the calculation and use some new approach. So this was 2021. So at the time there was not yet neural network quantum state. So we tried to redo the calculation that has been done here, just focusing here and see what happened. And we did this using what is called the neural network quantum state. So I will introduce them. I think that maybe some of you could be interested as a new numerical approach. Again, as always, nuclear physicists are very good in stealing what people in atomic physics does. So this was actually invented in atomic and condensed matter physics. So we just use it and again, and and I'm gonna show you some result. I don't, but I'm gonna be kind of fast. I just want to introduce a little bit how it works, and then I'll show you some result to understand somehow how the physics at the unitary limit impact the nuclear physics at the physical point. They are very preliminary, and I still am discussing with Alejandro about them. So it's just to give you an idea that what you are actually studying is really important for us to understand what is going on at the nuclear physics level. So regarding the neural network quantum state, so this is a classical variational Monte Carlo wave function. So you have fermions. We deal with fermions, so we need a Slater determinant. Typically, we put more, and then you put some correlation function in front. This depends on some parameters, the correlation function, and typically also the orbitals inside the Slater determinants. And what you do is just variational calculation. So you try to minimize respect to the coefficient, the energy. This is what you do with variational Monte Carlo. And if you do that, you obtain the correct wave function. Clearly, this is not super simple because you should. The problem here is that the correlations are very strong in the nuclear interaction. So what happens is that this correlation function is not necessarily completely flexible to describe completely the wave function. So it's not super flexible. So the idea of neural network quantum state is very simple. Instead of using like a constructed wave function, you use a neural network. So there is a theorem that says that if you have kind of an infinite neural network, you can practically reproduce any quadratic integral, practically any wave function, any function that is that you can integrate. So you can use a neural network. So the idea is very, very simple. As input of your neural network, you have the position, the generalized position, so position, spin, and isospin. You go pass through the neural network. And what you have at the end, your neural network is going to give you the value of the wave function in that position. What you don't know are the weights of the network that becomes your variational parameter. How do you get that? How do you get these weights? Well, the idea, again, is you just minimize this quantity here. And to compute this quantity, so this is a big integral, we just use the Monte Carlo sampling. So this is how it works. It's very weird. I know that at the beginning it took me also a while to understand. But the neural network is very flexible. And you see that the correlation are practically generated inside by the connection of the nodes. So I will probably skip also because for time I don't think is really worthy, but if you're interested, I can talk with you later. So clearly, we want to give some structure to the neural network, but so the wave function is actually already written kind of as Slater determinant as well, so that we enforce antisymmetry. But to the standard Slater determinant, we add some lines and some rows that are called hidden nucleon. So we have like more flexibility. And practically, each of the terms that you see inside here, just let me show you an example. Like, for example, the term up there are actually described by a neural network. So we actually don't have a big neural network, but we have a small neural network that describe each of the, for example, the orbitals or the hidden orbitals as well. So it's written in a very fancy way because we want both phase and a magnitude for the amplitude. So the neural network actually gives us like a real and imaginary part. But this is just technical details. The idea is that you break out the problem in several neural networks that are optimized all together. This again a technical detail. The only thing that is important is that for the part that is hidden orbitals, we have to break down. So we want that to be completely permutational invariant. So the neural network that we use is a little bit more complex. Again, if you are curious, then we can discuss as much as you want about this. How does in practical it works? It was like that. So we start at the beginning with a random set of weights in the neural network. We compute this quantity, so the energy, and then we have a rule to determine the new weights. So we just compute practically the derivative of the wave function with respect to the weights. So the cool thing is that if you use any kind of neural network, I don't know, like I use JAX, but the other is PyTorch, this thing is done automatically. So you don't have to code anything. You just ask them to do it for you. Clearly, we implemented that and optimized in a different way. And we repeat this operation several times. And you see that each point here is practically one of the calculation of this. And increasing the number of optimization steps, at a certain point, we arrive to the ground state that, by the way, in this case, was computed using hyperspherical harmonics. That was what I was doing during my PhD. So, and you can repeat this operation for any nucleus, technically. Another couple of things about neural networks. So this is kind of how it works. And again, it's just, so the error bar is associated with the fact that we are using Monte Carlo sampling to compute this quantity. So you understand that after a certain point, we cannot optimize anymore our wave function because we are below the noise generated by the Monte Carlo sampling. You can do something better because you can enforce parity before. So the neural network is learning everything. But like discrete symmetry are terrible to learn because you should have the configuration like for parity, the R and minus R. So you can enforce it, and enforcing like the discrete symmetries at the level of like the construction of the wave function, so at the level practically of the neural network before the optimization, you have actually you're doing a better job. So the optimization is much faster. It's just to tell you that you can be smart using neural networks. You can be even smarter. So one of the problems is, as I told you, so we add this hidden nucleon. Really, you can add as much as you want, and the more you add, the more correlation you include, and so the better it is your result. You see that this is the binding energy of oxygen 16, and you see that you have to arrive to 20 hidden states. The problem is that 20 hidden states means that the neural network is already huge, and the optimization is more expensive, et cetera, et cetera. So actually, the people in Argonne that I was working with came out with a very smart way to include some correlation already at the level of the spin, isospin, and position that you give that. It's kind of, again, I even don't know very well completely all the details how this thing works, but the idea is to practically use this. So these are the standard spin, isospin, and position. But what you actually give to the wave function is something that is already passed through a neural network that practically learn the correlation. And if you use this, you see that you just need one hidden nucleon. So this neural network is much smaller than having like several of that, and the convergence is incredibly fast. So with one hidden nucleon, you have a better convergence. So this is all calculation using the auxiliary field future Monte Carlo. You see that one hidden nucleon with this, it's called message passing neural network interface, outperformed the auxiliary field diffusion Monte Carlo. This was the best result ever in the world before the neural network came. What we did was to compute. Okay, I have another 15 minutes less. The binding energy of several nuclei. So the first point, using the interaction that I showed you before, so very simple interaction. And the result was kind of impressive because, first of all, we get within 10, 20% also all the binding energy of this nuclei. And with a very, very simple interaction. Remember that we are using practically 2 Gaussian.
I'll just do a sanity check. So the previous element is your training data set, right?
What?
Training a neural network for this helium-3, helium-4, and the oxygen.
So your training data set, we train, so every time for each nucleus, you have to repeat this operation. So the thing, it works like that. I'll go back, doesn't matter. Doesn't matter. I know, it's weird. So we don't really have a training data set. So what we generate is some configurations using the standard Metropolis hasting algorithm. We use this configuration based on the wave function that you have at the beginning. So you start with the wave function that is completely nothing to do with your Hamiltonian, and then you compute the energy. but the new wave function is closer to your one, so you generate a new configuration, sample a new configuration that is going to be your training point at that point, and you compute again the energy, and then you repeat this operation. Clearly, the sampling at that point are going to become closer and closer to your wave function, so you're going to get like self-converging system. So it's, I know it's very weird. It took me a while, but what you see at the end is this kind of convergence. Okay. So this is kind of impressive. I mean, we didn't expect to actually be able to reproduce so many nuclei with, I mean, maybe oxygen 16 and carbon 12 was okay, but it was kind of cool to see that this simple interaction it does practically 90% of the job, literally 90% of the job. So we use two different range for the three-body forces, but like a reasonable range just to show you that. So there is clearly some dependence, but it's really within, let's say, the error that you expect from a leading order calculation. So there are nuclei that we are not able to reproduce. I mean, a lot of these are really related to how the nuclear interaction, the details of the nuclear interaction are. So remember that there is also Coulomb force, so usually there is fine tuning. So a lot of these nuclei really break up, but let's say the main nuclei that we were expecting to reproduce, we were able. So another very important point is that we didn't do any kind of pre-training of the neural network. That means that we didn't like impose some form of the wave function. The neural network itself was able to learn somehow the nuclear structure. So the fact that nuclei have shell and are able to reproduce the oxygen 16 directly from the interaction. So there is absolutely no, so we didn't impose any kind of, except the anti-symmetry, but there is no like Slater determinant. And that was really, really cool. In general, this can be applied to as many nuclei. Clearly, the computational cost grows exponential. Well, not actually exponential. It goes actually as a power law a to the fifth. That's the actual thing. We also computed charge radii. Again, it's kind of the thing that we expected. So I don't want to comment much. But clearly, you tell me, well, you compute binding energy. How are you sure that you compute the shell structure? Well, the only way we can do that and check that if we are doing a decent job is to compute some other observable that is directly related with the shell structure. And in particular, we compute what is called the magnetic moment of the nucleus. And when you compute the magnetic moment of the nucleus, you have to compute the wave function that appears here in the bra and the cat at the total angular momentum projected along z that is equal j. So one problem is that the neural network has, since the angular momentum along z is a symmetry of the Hamiltonian, so it commutes with the Hamiltonian, the neural network doesn't learn that. So when you compute jz, and so we finish our training, you compute the angular momentum along z, and you get some number here. Absolutely random number, because the angular momentum of the nucleus is absolutely random. And so we learn from the people that does experiment how to polarize nuclei. So you add just a magnetic field. And this is exactly what we did. So we add to our Hamiltonian a magnetic field, and we start, see again, we optimize again the wave function. And you see that the angular momentum start to rotate. And here's very cool, and certain point you pass, so this is what you expect, the horizontal line is what you expect for lithium-7. And you see that at a certain point we pass this point. This is because in our wave function, actually, we have some extra contamination of higher angular momentum j. So lithium-7 is 3F plus, so our optimization is not perfect. So we have some extra contamination, and when we add this term in the Hamiltonian, this extra contamination gives us some extra excitations. At that point, so what we did was, okay, we have this extra excitation, what can we do? We can continue optimizing the wave function, turning off the magnetic field. And at that point, we get rid of this term here. And you get with at that point, you see that the nucleus remains polarized along the direction that you're interested in. And now we can compute the angular momentum. So if you look at the point of view from the energy, again, we are computing energy, so that's what we are optimizing. So what you see here, we turn on the magnetic field. So we have the process in which the magnetic field is on. So if we remove like in a perturbation theory, this matrix element from the energy, you see that actually our energy is slightly growing compared to the beginning. And this is this kind of excitation that you get because there are contamination. As soon as we turn off the magnetic field, you see that the optimization return again to the ground state, that the binding energy of the ground state that we've seen before. So it's kind of something that we figure out. I think it was just cool to show you because it's kind of simple, but pretty cool to see it. And it permits us to compute actually observable for nuclear physics. So, and I think that similar problem can happen also in atomic physics too. So you tell me, somebody has a question about the contamination. So how do I know that there are contamination? I know that because after all this work that I've done, the wave function was constructed in a different approach. And using this different approach, the optimization is much better. And practically is much better. And we are able to reproduce the ground state of nuclei with much more confidence. And practically you don't see anymore the contamination. So the piece that passed the 1.5, it disappeared completely using new configuration of the neural network. So this was really the first work that we did with this. So the cool thing is that we compute the magnetic moment and we are able to reproduce exactly, except for helium-3 and tritium, because other nuclear physics effect. But the magnetic moment of nuclei, and again, it's not that we are doing a great job because the interaction is perfect or we are not missing any term inside. It's mostly because we are describing the shell structure of nuclei. So that's like a proof that we are describing the shell structure of nuclei, nothing else. Okay, this was how things works. Perfect. With Alejandro, so what Alejandro was interested is like, okay, let's try now to do this calculation at the unitary limit and see how the spectra of nuclei look at the unitary limit and then evolve them at the level at the physical point. So here are some calculations done by the Quantum Monte Carlo group in St. Louis, actually, so not using neural network, but I wanted to show you like, so this, for example, is lithium-7 that is unbound at the level, so this is the threshold, the dashed line, is unbound at the level of the unitary limit, but as soon as somehow we break a little bit the symmetry that appears at the unitary limit, we have the lithium-7 bound. And this seems to happen several times. So with the calculation that I've done, so these are like for several nuclei, so this I did with neural network quantum state. Similar thing happens. So the calculation at the unitary limit are the blue one, and the empty circles are unbound states. And you see that at the unitary limit, practically the bound states are the carbon-12. And there's oxygen 16. So the nuclei after carbon-12 start to be bound at the unitary limit. While when you practically go to the physical point, a lot of them became bound. So somehow the thing that when we were discussing with Alejandro, that's the final thing that I want to say, is that nuclear physics have some some residual of the symmetry that appears at the unitary limit, because you see that more or less the structure is practically the same. It's just shifted down. So, and what Leandro is saying is really what is supposing at least is that there is the symmetry that appears at the unitary limit are actually somehow mirrored at the level of the physical state, and we are trying to see if this is actually working, and this seems to work. So I have finished. I hope you enjoy. I know it's a very weird talk, but please, any question?
Thank you, Alex. Time for a question, please.
Thanks. Very nice talk. So I think the reason why the neural network state works for this kind of physical context is because that some of the coupling constants, they are renormalizable. So my question for you is that for your last graph that you showed.
Okay, so this is one, right?
Yeah. So for these kind of that physical quantity with respect to all different nucleus, have you like compared your result with some RG result, for example? In terms of, like mass scaling or whatever?
So the answer is not. So I have to say that I don't know if the theory as it's written by Alejandro is fully renormalizable. I don't think so, because this was not a thing that Alejandro was looking into. But I have worked with another couple of people from Paris that asked me a similar calculation, where actually they did the theory renormalizer. So what we did there was to compute the next leading order and see if we are within the error bar of the leading order and stuff like that. And they had to, it was very tricky how they did it, but practically they have to introduce a range at the leading order. At that point, the results became comparable. So somehow I mean, I'm not super expert on this though, but what Alejandro is saying is like, forget about everything else where the theory comes from. If you're able to reproduce the effective range and the scattering length, you somehow, you know that you are in the unitary limit, so you forget about where the interaction comes from. Well, nuclear physics is there, so the symmetry somehow is able to reproduce the nuclear charge within 10-20%. That's what Alejandro is saying. And for me, it was kind of cool to see that, this is unitary limit, this is not, it was kind of the same shape, but even if shifted. So that's, I don't know, I know that they maybe didn't answer very well your question though. But the answer is I didn't do it. So.
Okay, yeah, that's good to know.
Yeah, I was interested in a lot of these results. One thing that puzzles me a little is why the physical model is more attractive than the unitary model, because at least for neutrons, the way you get from the real interaction to the unitary limit is by making it more attractive. Is that not true for the proton part of the interaction?
Okay, because there are two pieces, right? Because there are two ways, right, that contributes to this. One is the 1s0 that is repulsive, one the 3s1 that is attractive. So I would guess that so when you go to the physical case, the 3s1 becomes more so the unitary limit, the deuteron is not bound, right? So you have to make the 3s1 more attractive. So that's probably what is happening. I think that in the neutron-neutron case, you don't have the 3s1.
Right.
So you have only the repulsive thing. So you probably that's why you need to make it attractive. That's my guess on that.
So the triplet is made more repulsive to go to the unitary limit. Is that what you're saying?
The triplet, to go to the physical case, you need it more. Yes. To go to the you have to make it. Yes. And by the way, this is what you see also. So the helium-8 is actually bound in the physical case because it's like the 4 nuclear. And this is not happening here, probably because there is too much repulsion in 1s0. Probably there's still too much repulsion.
It's interesting that helium-6, we also calculated that in our paper this year, is you said it's unstable to cluster formation. That's at unitarity, it's unstable.
So it's unstable at the level of the unitary limit. It's stable here, but there is no Coulomb force here yet. So as soon as you add the Coulomb force, this in this theory becomes unstable as well. It's like at the threshold. It's always like again, this is kind of fine-tuning thing, I think. While you see here these nuclei that are actually the ones that are stable here, if you remove if you add the Coulomb interaction, they go practically on the top. That's the. So yeah, this interaction was without any Coulomb interaction, so it's written there. But,
it seems not so easy to do scattering calculations with this method.
No, so there is some. So this method looks very similar to what is called the Gaussian process. The Gaussian. Oh my gosh, I forgot the name. Where you like the wave function is constructed using Gaussian. I remember the Japanese work on that a lot. So because the Gaussian process is practically a neural network that is not yet a neural network. And they did scattering, putting everything like in a kind of a box, and matching that. So I never did it. I don't know. I don't want to comment because I really never did it. I don't know what is the quality. But it's how people start to think how to put everything in a box, compute the...
You mean the Lucier formula?
Yes, the Lucier formalism, yes. Like like...
There's something you might think about, which might be ideas of the scale too, would be to use your method to calculate the hyperspherical potential curves and couplings.
That would be cool.
Scattering on those.
That would be cool. That would be cool. I mean, I'm sure that Alejandro would be, I mean, I would be interested too, and luckily my work is Jefferson Lab that is completely out of where. but I have fun with Alejandro sometimes when he asks me stuff like that. So, but for sure, I think it would be cool. No, it's a very cool idea.
Questions?
Okay. Oh,
I have
okay.
So I like very much this neural network idea, but when you calculate the wave function, you're always using the variational wave function, right?
So the wave function is actually the neural network. So what? So when so this is how you would write normally, right? There are some parameters. So now forget about the parameters, and now the parameters became the weights of the wave. From the point of view of the calculation of the energy, you use a simple sample like before.
Yeah, but for that sampling, are you assuming any particular functional?
No, that's the thing. That's the thing. So at the beginning, you start with whatever is this. You have a random set of weights, so it's that random variation, but it self-evolves somehow in the right point. So at that point, the samples are always closer and closer to actually the sample that you will get from the wave function. That's how we put some limit, right? We don't want to go crazy. So there is some Gaussian approach at the beginning, but we don't have any kind of set where we start at the beginning.
How do you enforce anti-symmetry?
Yeah, sorry, I skip a lot, but practically the anti-symmetry is enforced because let me see if I have like a better one. So each of these pieces is actually a neural network, where there are, I mean, if you have like...
Well, the orbitals are the neural network, not the full...
Not the full, no, because I'm pretty sure that the neural network would learn slowly that thing, but the convergence would be so slow because it's a discrete symmetry, like anti-symmetry. So you have to change the position of the particle to have anti-symmetry, and it's not good for...
But then isn't it kind of obvious that the shell structure has to come out?
So the thing is like maybe that's actually a good. Remember that after that you run the neural network. So let's say this is kind of, so we use the Slater determinant, but this object here we call it orbitals are not orbitals anymore. Then when you optimize the neural network, it completely forgets the meaning of that. So you don't know what there are. So I cannot say, oh, this is like the first term in the Slater determinant, this is my first orbital. It's not like that. It could be anything because the neural network is optimizing itself. It could depend on how you started. So remember, so this is like the actual expression of the orbital inside. It's just a value that is there. So it loses somehow the knowledge, like the physical knowledge. The only thing that remains is that it is a determinant, and that's all. The determinant enforces anti-symmetry, but not the shell structure. So this.
Okay, now I'm hopelessly confused.
It's very weird because I mean, so we think it in normal physics term, and that's true. But as soon as you turn on the machine, you completely forget any kind of what is the meaning of the object that you have inside, because the neural network, is organizing the weights in a way. But I'm sure 100% if I start at a certain point with a random weights and then I start with other random weights, the value that I've got are going to be probably different because the optimization goes in different paths. They arrive at the same way, but it's also the weights could be different somehow. It could be more than one configuration of weights that give you the same minimum. That's my guess, at least. So it has no like a physical meaning anymore. And that's the bad thing. You don't have any. So looking at the wave function as it is, you don't have any other information. And again, and this is like the old version. Right now, we don't use it anymore, this one. We use a version that is called Pfaffian, that is like the square root of the Slater determinant. that I learned a few months ago too, and I'm not an expert at all because I just use it. So I just try to learn it. So, and again, it just works better. So this is just optimization. So everything that we did was just to optimize it, nothing else. To spend as less money as possible to compute this thing, practically.
Any more questions?